back. We got one more video here. You know what? It's more circle again with a pressure vessel, a thin wall pressure vessel. And guess what? This would be called a combined loading problem. Okay, this has got to be like a world record. Okay, for the most number of videos on Mohr circle with combined loading. Y'all are so bad at it. I had to do another one so you could practice. Okay. there's gonna be one more after this, and that's gonna be in the practice problems for this section. When you're practicing for the exam, go work on those practice problems. Let's see if you can knock it out. Right. All right. Here we go. We got a pressure vessel. What's going on here? We got a pipe with two ends screwed onto it. Right. Whoa. This looks kind of dangerous, nefarious even. Okay, but it's a little pipe. It's only a 1/2 inch diameter, so it's a little bitty pipe, about, you know what, I don't know. Let's say it's 6 inches long, doesn't matter. And then it has a 0.025 inch wall thickness on it, okay? So we're asked to determine the principal stresses at point A and the maximum shear stress at point A. So, can we do that? Can we draw the principal stresses and can we find the maximum shear stress at point A? That part sounds just like the last video, sounds like Mohr's circle, right? So what our goal here is, in the end, is to create us a stress element, right? Stress element, okay, of point A. Not stress element, this is stress element of point A, okay? And then it's going to have maybe sigma stress on it, okay? And then it might have some shear stress on it. So our goal is to find out if that's true, okay? Now how do we do that? Okay, so what do we got here? So we've got two end caps that somebody has screwed on. They put a torque on there, 20 foot-pounds, a moment, okay? And then also at the same time, there's a stretching force. There's a force trying to make the thing get longer, okay? And point A is right here in the center of this. So we've got a pipe here that's got two torsions on the end of it. It's got two end caps. Somebody screwed the end caps on there, okay? At the same time, there's some kind of force that's just trying to pull the end caps off. So there's a stretching force on the whole thing, right? And there's an internal pressure inside the pipe of 500 psi. And so here we are at point A. Point A is just a point on the body of the pipe on the outside, okay? And we want to find out, what's he feeling? What's the stresses there? Now remember this, okay? We've got two things. We've got a tau to find, okay? And we've got a sigma stress to find. There's a sigma x, there's a sigma y, okay? And generally we can say a force can create any of these things. One force can do any of these things, okay? It can create P over A stress, just stretching or compressing. It can create bending. We could create VQ over IT, transverse shear, or we could create TC over J, okay? TC over J, what is TC over J? TC over J is the torque, the shear stress from torsion, okay? Now, in addition to that, we have our old friend thin wall pressure vessel problem here. You can have sigma stress also on those from PR over T and, let's see, what's the other one called? PR over 2T. Okay? What is this one here? This one is hoop. There it is. Hoop stress. And this is longitudinal stress, okay? That stress over there is the one that's trying to push the end caps off from the pressure. This one here is the one that's trying to make the diameter get bigger, okay? So, let's see what we got. All right, point A. All right, let's talk sigma x, okay? Sigma x. What is trying to make the thing stretch, okay? Well, number one, this force here, okay? Now, here's a good thing that you can do, right? Is just chop the thing in half, right? if we section it, cut it at point A, we can find the internal forces at point A and what's going on there, okay? But one of those is, what's the force on point A? How many of you think it's 400? 200 plus 200. Johnny Weeksalsh, raise your hand. And no, good. Okay. Remember, cut it in half, so cover it up. What's the force on that? 200. So what's N going to be to oppose it? 200. Okay. So sigma in the X direction, all right, is going to be what? It's going to be the force, 200 pounds, divided by the area. What is the area? Oh, lordy. Okay, the area is this. Area equals, well, it's pi r squared, right? Well, it's pi r squared inner minus pi r squared outer, or pi times r inner squared minus r outer squared, right? Which is going to be, let's see, A equals pi times the, well, you did that exactly backwards. It's O minus I, not I minus O. Okay. Don't do it like I do it. Do it the right way. Okay. Okay, so what is the outer diameter? Or, I'm sorry, outer radius. And I was given diameter, wasn't I? 0.25. Okay. Is the radius there minus squared minus what? Ooh, 0.025. How much is that? That's 25 thousandths of an inch, right? So on, clear my calculator, this calculator. 0.25 minus 0.025 makes that inner radius 0.225 squared, okay? And so the area is equal to, what is that? 0.25 squared plus answer squared equals, no, minus, not plus. My brain is not working right today, y'all. Can you identify? That's every day for me. I know, right? Times pi. Oh my goodness. I got 0.0373. You better check me. Okay? 0.0373 inches squared. Okay? All right, so here we go. 0.0373 inches squared. Now that's going to give me PSI, isn't it? And that's in tension, right? Is that in tension? Whoop, whoop. So that's a positive, isn't it? Okay. Do we have any bending here? Is there any bending on this pipe? Well, the answer is no. Since the 200 is pulling straight in the middle, there's no bending on that guy, right? So there is no MC over I. That guy doesn't get to play. Okay? The next thing is there any VQ over IT stress? Well, in order to have that, I would have to have a V, right? And if I cut this beam in half, remember V would be going in the perpendicular direction, up and down. What force is there that's going to cause an up and down shearing force? There isn't any, right? So V would be equal to 0. So we're not going to have any of that, right? None of you. Are we going to have any of this, TC over J? Yeah, we are going to have that, aren't we? Okay, let's calculate that. Tau XY equals TC over J. And the T is what, 20 foot-pounds? Okay. Now I think right away, I got to get rid of those feet. I got to get rid of that. So I'm going to put a foot on the bottom and 12 inches on the top. The feet will cancel out. And that'll give me everything inches. Then I got C. What is C? TC over J, right? TC, what is C? C is the distance from the neutral axis or the center of the thing out to the point of interest. And our point of interest is on the outside of the part. So C is actually just a radius, isn't it? It's 0.25 inches. Okay? Divided by I. Oh no! It's I for a, no, it's J. It's not I, it's J. Oh goodness. We don't want to get this backwards, do we? Is it J? Because J and I are close to each other. One's pi over 2 r to the 4th, and one's pi over 4 r to the 4th. So which one is J? It's the pi over 2, isn't it? It is pi over 2 Remember, it's r to the fourth outer minus r to the fourth inner for hollow shafts, which is what we have. So it's those two numbers right there. But instead of to the square, it's going to be to the fourth, right? So 0.25 to the fourth minus 0.225 to the fourth. Okay? And that's in inches to the fourth there. So we got an inches and an inches there. That's inches squared. Those go away. That's going to leave us with an inches squared on the bottom. Pounds over inches squared. That's going to be in PSI, isn't it? All right, let's calculate that number. So what is that number? 0.25 to the fourth, okay, minus 0.225 to the fourth equals times pi equals divided by 2 equals, oh, little bitty number. Okay, I got this number in my calculator now, and then I got 20 times 12 times 0.25 equals divided by that last number there, which was 0.00211. Enter. Woo! 28,436. What is that? That's PSI. Woo, that's a lot. Or we could write it like this, 28.4 KSI. Okay? We're going to be getting pretty close to the yield strength of that material there, aren't we? That's a lot. Okay. It's really thin though, 25 thousandths of an inch. That is really thin. That's like Coke can kind of thickness there. Okay? Now, what about this guy, sigma x? Are we done with sigma x? Or is there something else that's going to cause a stress in this direction? Well, yeah, this guy down here, right? PR over 2T. That guy is the longitudinal from the pressure, which is trying to push the end caps off, okay? So since it's a positive pressure and it's trying to make the thing get longer, it's also going to be positive. So let's just do a plus, right? And let's put that guy in there, PR over 2T. So the pressure, 500 PSI, okay, times R, what's the radius? Okay, what's the radius? This is a tricky one, right? From that equation, do you remember this? Where is the pressure? On the inside. So is it the outer radius or is it the inner radius? It's the inner radius, okay? So that's 0.225, and that's inches, right? Inches. Oh, smudgy. Okay, divided by 2T. 2 times the wall thickness, 0.025 inches, all right? Now guess what? Those 2 inches are going to cancel out. That's in PSIs. That's in PSIs. I think we got it, don't we? So sigma x is equal to what? Sigma x is equal to 200 divided by 0.0373, which is 5361.93, okay, plus 500 times 0.225 equals, divided by 2 equals, divided by 0.025 equals, 2250. Okay, which when I add those two together, plus 61.93 gives me 7611.93. Okay, and that's PSI. And that's my sigma x. So that's what's going to go, sigma x, right there. How about we do this? 7.61 KSI. Tau xy is 28.4 KSI. And then what is sigma y equal to? Who's causing stretching in this direction? Only one guy, and it's that guy right there. It's hoop stress, right? And it's also going to be positive, isn't it? So positive, 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 okay? So here we go. Sigma y is equal to PR over T. So 500 times R, 0.225 divided by T, 0.025 is equal to how much? Okay? I bet it's going to be twice as much as that, don't you? Let's do it. 500 times 0.225 equals, divided by 0.025 equals 4,500. Guess what? It's 2 times that, isn't it? Or 4.5 KSI. Okay? Are you with me? We have done now the combined load business to come up with a stress element. All of that work over there and this over here was just to come up with that. No, there's one thing missing here. Oh, let's get this. Which way does the tau arrow go? It won't affect your answer here, but let's get it right if we can, okay? So here's this side of the pipe, right? Here's this side of the pipe. We're going to split it, and here's A. There's my little stress element, right? So over here, guess what? I got a torque that goes this way that's causing the shear. So on this surface, it has to go this way. So on this surface, it has to go that way, then this way, then this way, and then what? That way. And look, bam, it does, doesn't it? So that gives me those arrow directions. Is that easy to do or what? Is that helpful? I hope this is helpful to you. We ought to be combined load experts by now, right? All right, let me erase my board and let's do the Mohr circle part and we'll finish this rascal up. All right, here we are back again. I moved my stress element over there just to give me some more room, okay? So step one for Mohr circle is what? Come up with 2 coordinate points, remember? Okay, how many times have we done this? We've done this a lot so far, haven't we? If you miss Mohr circle in the test, I'm going to come find you. Come on, we got to be doing good, right? On the X face, I have what? 7.61. On the Y face, I have 4.5. And then the tau on the X face rotates me clockwise. That's negative. So minus, 28.4, right? 28.4 and positive 28.4. Okay? So this is my X face. This is my Y face. Okay? So we want to find what is the max shear stress, and we want to find out what are the principal stresses. Let's go. Let's plot that, okay? Let's plot it. Woo, long line. Here we go, sigma, okay? Not X, just sigma. Okay. Tau. And remember this down here is tau positive. That up there, that's tau negative. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8. Whoa. 7, 8, 9, 10, 11, 12. Okay, so can we plot this? Let's see what we got. One coordinate is 4.5. 1, 2, 3, 4 and a half is here. Okay, it's not going to make it very big, is it? And then the other is 28.4. I don't know. Let's see. What are you going to do these in fives? 5, 10, 15, 20, 25, 28 is somewhere in there, right? And it's 4.5 positive 28.4. So there's 0.1. That was from the Y face. And then the other one was what? 7.61. 1, 2, 3, 4, 5, 6, 7.61 is in there somewhere. And then 5, 10, 15, 20, 25, 28-ish is like there, okay? So here we go. Oh, that's pretty good. That's pretty good. Okay, so this one up here was 7.61, negative 28.4. And this one down here was 4.5, 28.4. Okay, make a circle. Make an egg. Okay, pretend it's a circle, okay? It's perfect. It's perfect. Where is the center? Okay, well, that's easy to find. It's 7.61, that point, minus this point, minus 4.5, divided by 2 will give me a number there, right? What is that going to give me? Let's see. Come on, calculator. Okay, 7.61 minus 4.5 gives me 3.11 divided by 2. So 3.11 is that whole distance there, divided by 2 is 1.555. So this is 1.555, and this 1.555. So where's the center? It must be at 4.5. 4.5 plus 1.555 equals 6.055. So the center is at 6.055. Okay? Now, what do I know about that center point there? Okay? Let's call that KSI. What do I know about that center point? That is also equal to sigma average. 6.055 KSI. There we go. We found something. They didn't ask us for that, but we found it. Okay? What is the value of sigma when I'm going to be at tau max? So when tau, the shear stress, is at the very maximum, what is the value of the sigma stress? Always sigma average. Because guess what? Tau max happens, bam, right there, one radius, right, above the average, doesn't it? Well, let's find that, tau max. How do we find tau max? I'll tell you how we find tau max. Is we find, what we do for that is we find the radius of this circle, don't we? Because what I need for tau max is I need this value right here. I need to know the radius of the circle. Well, here we go. Right? The radius is equal to 28.4 squared plus 1.555 squared. So 28.4 squared plus 1.555 squared equals inverse square root second. Answer equals 28.44. 28.44 KSI. Okay? That's what tau max is. 28.44 KSI. Okay? Bam! All we're missing now is the principal stresses. And remember, here's one over here. That's sigma 1. Here's one over there. That's sigma 2. They're super easy to find because all they are is this. All they are, let me erase this, is, I'll erase this too, I'll work it right there. Sigma 1, sigma 2 is equal to the center point, which is 6.055, plus or minus what? Plus a radius to get to him, minus a radius to get to him. And the radius is right there, 28.44. Okay? And so, sigma 1 is equal to 6.055 plus, oh Lord, where's plus? Plus 28.44. And that one is 34.5 KSI. And sigma 2 is 6.055 minus 28.44 is negative 22.4. And there are your principal stresses. Now, when you're at principal stress, when you're there, what's the value of tau? Huh? When I am here, what's the value of tau? Well, tau is 0, right? When I'm here, tau equals to 0, right? When I'm here, tau equals to max. All right. That's a little more circle. That's a little combined load problem. That's a little pressure vessel. That's a little bit of everything, is it? Good test question, huh? All right. Hope this helps, and I'll see you on the next video.